Number 1 in chapter 18, we introduce you to equilibrium. So up to this point, we have had a reaction. Looks like this. Arrow goes one way. We are now going to get 2 arrows in our equation with equilibrium. So we're going to use this example quite a bit. So far, we've said, hey, previous examples, nitrogen and hydrogen react to produce NH3 or ammonia, and that was it. Now we're going to have NH3 break down into an H2, and all this is happening simultaneously, okay? So what we have here is what we refer to as chemical equilibrium. Questions? All right, so with chemical equilibrium, we have what we call reversible reactions. We have a reaction going from left to right. That's traditional, right? You've seen that. And then also, now we have this new part. We have the ammonia, NH3, which traditionally is going to be referred to as our products, is going to break down back into our original reactants. We put those together, and we essentially have these, what I call half arrows, left to right arrow, right to left arrow. Both reactions are happening at the same exact time. So think of this as I-55 over here, right? It's an interstate, and you have cars going north, and you also have cars going south. At equilibrium, technically, we would have the same number of cars going north as we would going south, okay? I do want to go over and write some things on this chart. I know we're going to go over them time and time again in these notes, but I want to identify a couple of things, and the first is this. Notice we have H2 and we have N2, okay? And so at the beginning of this equilibrium, we have our reactants are present at the start of the reaction. Then down here on the bottom, I'm going to highlight it here in, let's do green. Down here at the bottom, this line is NH3, which is our one and only traditional product. And notice that our product is not present at the start of our reaction. Okay, so our product is not present at the start. Hello? Hey. Yes, I'll send them down. Will do. Yep. All right, so we have, again, reactants. They're present at the start. No products are present. Then this dotted line represents that we have reached equilibrium. I want to point out, and I'm going to write in pink here, this. Notice at equilibrium. At equilibrium, we have 3 things that are happening. Okay, so at equilibrium, which is that dotted line, at equilibrium, we have 1. There is both reactants and products present. Two, the concentrations are constant. So I'm going to do this. The symbol for concentration is just brackets, okay? So I'm going to say concentrations are constant. However, this is a really important point, okay? We have some of each thing. We have concentrations that are constant. But notice, H2 has a different concentration than NH3 and N2. So concentrations do not have to be equal. They have to be constant, but they do not have to be equal. So I'm going to put this. Our concentrations are not equal. They're constant, but they are not equal. Okay? I'm going to emphasize this. It's written in notes, but essentially what we're going to go over in the next couple of slides is summarized in this point. So we have some reactants to start. No products at the start. We make the reaction go. We reach equilibrium. At equilibrium, concentration, the sum of each thing, reactants and products, they are constant, non-zero, and then they are not equal. They can be, but they don't have to be equal. Questions? Does anybody need this? Yes. Okay.
Freaked out, sir.
Don't hit a car.
I did not hit a car. Jackson Plum thinks I hit his car, but it wasn't me.
Who does?
Jackson Plum thinks I hit his car. It wasn't even me.
It made them look pretty suspicious.
Because I like, okay, this is what happened. The car that hit it, and Jackson Plum pulled off into a side party car. So that's what happened. I gas right out of the parking lot. So it makes it look like I hit his car. I'm freaking out.
I mean, I was in the car with them.
And then it gets all, it says, I'll shut it down.
What car is it?
Purple water.
Did it happen today?
I happened Friday.
Oh, it happened on
So
Friday.
put them together. They produce this.
I believe I'm forward.
And now produce it back to the.
Wait.
So again, think of it like a two-way street. You're headed that way.
So it's the product reactor.
And it'll make more sense as we go along. We'll go through this. All right. Anybody still need it or any other questions? Okay. Moving on here, we're going to go a little bit quicker. Number one, at equilibrium. Technically, the definition is the rates. The only thing that are equal are the rates, not the concentrations, but the rates. So again, let's use our two-way street for our I-55 example. Substances moving north, moving at the same speed as those substances moving south. And there's the same number of cars going back and forth, north versus south. Okay? Rates equal. Now, rates, we saw this in chapter 17 with reaction rates and kinetics. That's where we get this value here. So let's break this down. At the beginning, we only have N2 and H2. They initially produce some NH3. Once we have some NH3, the NH3 then breaks back down to N2 and H2. And that's what this next slide says. Okay, reaction proceeds, we get some NH3. That NH3 then breaks back down into N2 and H2. So again, think of that two-way street where we have reaction going left to right, and that reaction going right to left. Exactly. North to south. Now, everything that I put on that graph under number 3, points C, D, and E, which probably should be labeled as points A, B, and C, all of those things, all of these things here are exactly what I put in the graph. So concentrations are constant. They are non-zero, which means we have to have some of everything. And they are not equal. All right? Really important points here under number 3. Anybody still need this? Questions?
Nope.
Okay. Now, equilibrium is this. All right? So it says it's known as the state of action. What this means is there is always a left to right reaction, and then we can turn around and go right to left. So we're always essentially having 2 reactions occur in one. One going forward, one going backward. Okay? Now, our substances. Yeah, iodine is going to iodine. You may think, not much is happening there. Well, in chemistry-wise, this is a phase change. A solid is going to a gas, and then backwards, a gas is going to a solid. So something is happening, although we're not having the transformation of an actual substance. Then we can have our expression written in this format. Number one, we've seen K. The K's can somehow be related, but I'm going to save that for a different class. Take AP Chemistry and we'll see that. This right here is a capital K, large, giant K. I like to put EQ to emphasize again, I am talking about equilibrium. Equilibrium.
I think that's a sign that we should.
Equilibrium.
I saw it TikTok, and this girl was talking about her least favorite things about chemistry, and equilibrium was one of them.
Yeah, it's a tough concept to grasp at first.
There's also-
Cool reactions though.
It also said stoichiometry.
You get it. All right, I do want to break this down.
6.0.
On our equilibrium expression, on top, substances C and D are what we would traditionally call on the right-hand side, what?
Connection.
How about reactants or products?
Products.
They are traditionally called products. This means on bottom,
Reactants.
very good. And you're going to hear me say this over and over and over again this entire chapter. Equilibrium expression. Products over reactants. Products over reactants. Products over reactants. Then, what's really nice about equilibrium is this. I'm going to circle in green. Circling in green are powers. Well, those are those little letters that come from the equations. So the powers are simply just the coefficients from our balanced chemical equations. This is nice because remember in kinetics or rate, we had to work to get to those values. Now with equilibrium, all we have to do is look at our coefficients. That's it. Questions? Does anybody need this?
Products will always be on the top.
Products over reactants. Products always on top for equilibrium. Yes.
Why can't it be reactants on top?
It's about our ratio, right? So think of it like this, and this technically isn't correct saying this, but we produce our products first. So we gotta produce those first. Then we reinvent this, we go backwards.
To see what your reactants were to make that product.
So think about it like a racetrack, right? You're walking, you make your turn, and now you're walking back. So you gotta go this way to be able to go that way.
Do we really need to do four
How
would you know?
It really is. All right, so here we go. What's the point of K? Well, the point of K is this. It tells us what substances dominate. Big K is meaning products dominate more products than reactants. Small k, less than 1, reactants dominate. What do we mean by that? There's more reactants than there is
products.
Very good. And that it's all about concentration, about that expression. Now, K does not have a unit. K occurs at a certain temperature, and we're going to use a giant, which I made that a bigger size, giant K. Questions?
Big K for Kelvin?
Not Kelvin. Don't confuse that. That's actually a good point. This is even bigger K. Yeah. Super size K. All right, so, hey, homogeneous equilibrium means everything is the same state of matter. Oh, by the way, the only thing that we can put in our equilibrium expression is gases or aqueous, AQ solutions. Solids and liquids are not in our particular expression. Now, what's this? Well, it's all about just stuff. Yeah, stuff. It's all about how these things are reacting and their concentration. concentration. So we can take concentration of gases, aqueous, liquids, and solids, all what we call pure substances. They all plainly surface. Now, if we have a K, which Dylan brought up a very important point. This is at 731 Kelvin. Our ginormous K is 49.7. Okay? 49.7. Is that bigger than 1 or smaller than 1?
Bigger.
So what dominates? Products or reactants? Products dominate. What that means when we say products dominate,
There's more products in the reactor.
yeah. There it is. And that's what it's interpreting. Questions? All right, let's go through this. Next example will be really fast. We want to write the equilibrium expression for this, and we're going to see this quite a lot for the rest of the notes. Guess what? I'm going to really emphasize this, and I'm going to say, hey, our equilibrium K is this. What's on top? Products. Hey, products. In brackets to represent concentration. That is a Q. Oh, that's Q. Yeah, Q. Try my Q. NH3, because that is our products. Now we look at the coefficient, and it's a coefficient of 2, so we raise it to the power of 2.
Oh, bracket N to
Over.
oh
Over. Now what's the first thing?
bracket
Yep.
N to
Into raised to what?
first.
First, which we don't write. Then we say times H2 raised to what power? 3. Good. This right here would be our equilibrium constant expression. That's it.
Oh.
See, we
These are gonna be the 8-point problems on the test, right?
It will be this, and you have numbers to plug in. Seriously.
Really? That's it? So it'd be like NH3 equals.
So I'll say
we would
like
find
0.1.
Yeah.
And you'll have to actually calculate it, which we'll do here.
So the only time you could.
was this test marked?
This is gonna be easy to do.
Truthfully, you guys will be the first taking an actual chapter test because all I did is push it onto the final. So what happened last year is it somehow spring break got involved and we were like halfway through and everything was all jumbled up.
You're
Do they just move slower than us?
Yeah,
Or just him.
We're better.
We're one of the-
We are them.
yeah. You guys are definitely at a faster pace than last year. All right, hey, here's really important. Remember, only gases and AQ are included in your equilibrium expression. So this is ethanol melting, liquid to a gas, vaporizing a gas. Notice here, okay, it's not in our expression. It can be in our equilibrium equation, in the expression it can't be. So only the gas is in here. Let's try an example with this. Yeah.
So we would have no.
Okay, let's try this. So we want the equilibrium expression for this. So I say KEQ. From the last slide, only things that are gases and only things that are AQ, aqueous solutions, can be included.
So we put.
Products over reactants. So we start here. Sodium carbonate, it has a solid. Guess what? Solids cannot be in here. Now, what do we do with CO2? We put it in a set of
brackets.
Very good. We raise it to what power? 1. We don't put it. So CO2 bracket. Cool. Times, what's our
H2O.
H2O?
No raising.
No raising it. Now, here's our deal with our reactant. It's a solid. We can't include it. If you cross everything out, which we only have one thing, which is a reactant, it's technically this stuff on top, technically over 1. Because if you put it over 0, it's undefined, right? Now, how you're going to see it written most of the time is without the over 1 business. You can write it because that's technically what you're doing. Most of the time, it's just going to be written, in this case, CO2 times H2O.
So then we would just do like 0.1 times 0.03.
Yeah, exactly. Yeah, you got that.
Oh.
Okay, now we get this.
Oh, no, got no.
Okay, now we got numbers. Now, Corbin brings up a really important point. You not only have numbers, but you have two numbers for the same substance, initial versus equilibrium. Well, guess what? Big K is the equilibrium expression. Equilibrium constant.
Equals equilibrium.
Exactly. Make sure you're going to put your values at equilibrium, or it's listed at equilibrium. All right, that's important, right? Notice.
Don't do that.
Well, okay, K is still a constant.
Yeah.
Notice all of these values here on the right-hand side are the same, or end up being the same. If you don't put them at equilibrium,
Yeah.
they will be all sorts of numbers, which is not correct.
Okay, so like when we're writing that K, we have to put the EQ, and if we don't, it just gets all messed up.
You don't have to put EQ, but you have to put the values at equilibrium. So again, if I try to put HI as 0, this would make it 0 over whatever.
Yeah.
It's automatically 0. So we have to start at equilibrium.
Like on the homework.
It'll be easier because I'll say at equilibrium. So, and not list a big chart like this. All right, so I put this in here kind of late here, but we already said 49.7. What dominated again?
That would be products.
Yep. And now, how about this? Products dominate. How about this? Now we have a big giant K, 4.6 times 10 to the negative 31st. That means 30 zeros are in front, and then you have the decimal. Really small number. So what dominates here?
Reactant.
Reactants. And again, it just means more reactants in terms of concentration are present. Okay?
That's all we have.
Yeah, I should have put that earlier in the set of notes, but whatever. Questions? Okay, anybody need it? Okay, great. You see what dominates or what's bigger. Wonderful. Now let's end this. So number one, I gave you the equilibrium expression, which we wrote earlier. It's our NH3, which is a product, raised to second power on top times N2 times H2 on bottom. Now, notice here we have some important points, is that all of these things are at equilibrium. So it says at equilibrium. That's the values we have to use in our equilibrium constant expression. So here we go. We're going to say this. We're going to say we want to know what KEQ is. So on top, we have NH3. The unit is 0.933 moles per liter, aka molarity. So in brackets, we're going to say this. 0.933 raised to what power?
The first or second?
The second. Remember, it matches what's up here in that expression. Now, divided by, and here's where we come into play with our other substances. N2 has a value of 0.533. So on bottom, I'm going to put in brackets 0.533 raised to what power? First. Then we multiply this. Now our value of hydrogen, which is
600.
Yep, raised to what power? Yep. Now, I get it that I write the power outside. I would view this in your calculator parentheses, but move the power inside. So what I do is this. I take 0.933 and I square it, and I get 0.87, decimal keeps going. I divide that number by parenthesis 0.533 times parenthesis, again, 1.600 root, caret symbol, to the third power, close the parenthesis, close it again because we started with 1, and I end up with 0.399. So our KEQ equals 0.399. Now, 0.399, do products or reactants dominate?
Reactants.
I heard both. Why reactants?
Because there's more.
Okay, if it's less than 1, it's between 0 and 1, reactants. More than 1, products.
So then, wait, so do they have like a certain?
Now-
put mole.
Check the, just think about it. You had 0.933 squared. which actually gets smaller. And then 0.533 times 1.6 root 3, that's gonna be a lot bigger number on bottom. That's what that's saying. There's a lot more of this stuff on bottom than there is stuff on top.
Do we have to put like, after the 399, do we have to put more?
No, that's a really good question. K is unitless. Unlike last chapter where you had all these different types of units, K here is unitless. You write it like that.
So reactant.
Reactants dominate because it's between 0 and 1. If it's more than 1, products dominate. Okay, any questions?